Hello, my name is Murray Hyde, and today I'll be talking to you about two complex hydraulic variables, Froude's number and Reynolds number, and how these two variables can affect the habitat preferences of freshwater mussels. I'll start out talking about Froude's number. In simplest terms, Froude's number is basically a measure of how tranquil or rapid a stream is flowing. More rigorously stated, it's a dimensionless ratio of inertial forces to gravitational forces. And it can be calculated using the formula F equals V divided by the square root of G times D. V here is mean velocity of the stream. G is the gravitational constant, which is just the acceleration due to gravity. And D is the hydraulic depth. In a stream system, or in a stream or river that's either large enough or has a rectangular cross-section, the hydraulic depth D can be substituted for just the mean depth of the cross-section. And that's when you're looking at Froude's number for an entire stream or river. When you're more interested in Froude's number at specific points, such as you might be if you were looking at Froude's number at a specific location of an individual mussel or a specific habitat point, you can use the mean velocity of that point and then substitute D, again, the depth of that point. The numerator, again, it's the ratio of inertial forces to gravitational forces. The numerator of velocity would be the inertial forces, and the square root of G times D would represent the gravitational forces. This one's pretty easy to understand, the velocity. Square root of G times D is a little less intuitive, but essentially it's a measure of, it's the speed at which a ripple or wave on the surface of the water that you might get, say, if you were to drop a rock in the water or place an object in the water. It's the speed at which that ripple or wave moves relative to the velocity of the water itself. So, using Froude's number, stream flow can be classified into three different types. When Froude's number is less than 1, the flow is considered, you have what's considered subcritical flow. It's by far the most common type of flow in streams and rivers, especially in your lower gradient streams where your elevation changes very gradually. In simple terms, subcritical flow are areas with are deep, slow flowing areas of the stream. In simple terms, a ripple or wave on the surface of a subcritical flow is able to propagate upstream. The other type of flow based on Froude's number is when Froude's number is greater than 1, and this is called supercritical flow, or more simply, it's just shallow, fast-flowing water, as opposed to subcritical flow, which is deep, slow-flowing water. A ripple on the surface of a supercritical flow is not able to propagate back upstream. If the wave is created, it can't get into backwaters. It flows immediately downstream. Supercritical flows are much less common than subcritical flows, but they are found more commonly in steeper gradient streams where you have sharp elevation changes. The reason these aren't as common is because they're really only typically found in nature, in areas such as rapids or around debris such as logs or rocks. Artificial sources of supercritical flows may be dams, weirs, and culverts and other things such as that, where you have basically anywhere where you have a sharp change in elevation. The third type of flow based on Froude's number is basically just a transition between the two. It's when Froude's number is equal to 1. The inertial and gravitational forces are equal. And it's really only found in transitional areas between super and subcritical flows. A ripple or wave on the top of the water in its critical flow area remains stationary. And a good example of such a phenomena would be the standing waves that you sometimes get in rapids, where you'll see kayakers doing this in some places, where they'll get in and they just go back and forth. And that standing wave is basically created by the critical flow between a supercritical and subcritical flow, where the wave can't propagate either direction. One last illustration that may help you to understand the differences between supercritical, subcritical, and critical flows is, say you were to place a stick or a finger in, I'm using a pen for illustration, to stick it just halfway into the water, and say the stream flow is going from this direction to that direction. In a subcritical flow, which is most common, shallow, deep, slow flowing water, when you place the object in the water, you'll get a V-shaped wave effect going on either side. You'll basically have a wave, standing wave, or not a standing wave, but a few ripples immediately upstream of the object, right around here, and then a V-shaped pattern of waves going downstream. In a supercritical flow, by contrast, your V-shaped pattern is much more pronounced, it's much narrower, and you have no ripples or waves upstream of the object itself. So the waves start at the object and flow immediately downstream without any propagation back upstream, and that would be supercritical. And then of course critical is the same as supercritical, except the V shape is at a 45-degree angle in relation to the direction of stream flow. Supercritical, one last thing about supercritical, subcritical, and critical flows are closely related to the phenomena known as the hydraulic drop and the hydraulic jump phenomena. When subcritical flow experiences a sudden drop in elevation, like so, the flow, it's a relatively steady flow back here, and then the sudden drop, the flow accelerates, and the water depth, say your water depth was down to here, but it's flowing over an object here, the water accelerates and the actual water depth from here decreases. And that would be your subcritical flow, your transition zone, and then your supercritical flow. At some point in here would be a critical flow point where where you would have a standing wave in certain situations. At the bottom, where this supercritical flow, eventually the gradient becomes more shallow again. So now you have the supercritical flow coming down, and when it becomes shallower, the velocity of this supercritical flow decreases, and at that decrease you have the hydraulic jump phenomenon, where the depth of the water jumps upwards. So you have the critical flow coming down, back to subcritical flow, and then a jump upwards, and then it levels back out. Now that I've given a basic overview of Froude's number and how it relates to supercritical, subcritical, and critical flows, I'm just going to spend a moment talking about how this might relate to habitat preferences of freshwater mussels. Freshwater mussels, compared to many other freshwater organisms, are relatively sedentary. They tend to burrow into sediment when they're able to, and they pretty much stay there or right within a small area unless they're disturbed in some manner, such as a high discharge event coming through and scouring out the sediment. For this reason, they do tend to prefer generally low flows where sediment's less likely to be moved. And at a given depth, a lower Froude number corresponds to a lower flow velocity, so you might expect a freshwater mussel to prefer areas that have low Froude numbers, even in comparison to other slow moving sections of the stream. There's some evidence that this is the case. For example, a study of federally endangered species in the Delaware River found that in 2 reaches, this species preferred locations, or it was found in locations where the measured Froude's number was lower in comparison to other sections of the stream. And in the third reach, it didn't show this preference at low and medium flows, but at high flows, it did show a preference for areas that had lower Froude numbers in comparison to the other areas of the stream. Most likely prefer these areas as a refuge during high flow events to avoid scour. Now that I talk about Froude's number and a little bit on its effect of habitat preference of mussels, I'm going to shift gears a little bit and talk a little bit about Reynolds number. Reynolds number is, again, a dimensionless ratio, except now it's a ratio of inertial forces to viscous forces. Whereas Froude's number is can be thought of as a measure of how tranquil versus how fast flowing a stream is. Reynolds number is essentially a measure of turbulence. It can be calculated using the inertial forces is the numerator here, where it's rho times v times r. Rho is the density of water, v is the mean velocity of the water, and r is the hydraulic radius. And then you divide the inertial forces by the viscous forces, and here mu is simply a viscosity coefficient. As with Froude's number, Reynolds flow can be divided into three different classes using Reynolds number. The first one is laminar flow, and this is found when Reynolds number is less than 500 or less. And at this level, viscous forces dominate over inertial forces. Laminar flow is very smooth and predictable with parallel streamlines. And by predictable, I mean that its behavior can be predicted using equations and formulas fairly accurately. And another way of thinking about it is laminar flow. You can think of it as sheets of water flowing on top of each other, but flowing parallel on top of each other, but never mixing vertically in through the water column. Laminar flow is relatively rare in streams, and it's usually only found at the interface between the water and some relatively smooth objects, such as the stream bed or rocks. It can also occur in areas such as when water flows through small openings between rocks, and you can also find it in stands of dense aquatic vegetation where the vegetation is thick enough to slow down the velocity so that viscous forces can take over. When Reynolds number is greater than 2000, you no longer have laminar flow, but instead you have your inertial forces dominate over your viscous forces, and you get turbulent flow. Compared to laminar flow, turbulent flow is far less predictable. It can't be predicted it can only be predicted statistically, but not deterministically. The water no longer flows in parallel sheets, and the velocities can fluctuate wildly, and there's mixing in the form of whirls, eddies, and other secondary patterns. And this type of flow is the most common in a stream or river. Again, like with Froude's number, you have a transition period. When your Reynolds number falls below 2000, there's a gradual shift from turbulent flow to more and more laminar flow until you reach pure laminar flow around 500. And this zone between 500 and 2000 is called the transition zone. As an example, remember that laminar flow is pretty common at that layer immediately above the stream bottom. As you get further and further away from the stream bottom, that you shift from a laminar flow to that transition zone, and eventually to a turbulent flow at closer to the surface as your distance from the stream bottom increases. Like with Froude's number, Reynolds number is also a potentially important variable affecting freshwater mussels. Again, they're commonly found burrowed into the sediments, and the only thing if you can see them at all, the only thing you can usually see is the in-current and ex-current apertures just barely sticking up above the actual sediment. So they're likely, or freshwater mussels are likely fairly used to laminar flow at that interface between the stream bottom and the water. So consequently, they're probably fairly likely to be to prefer areas with lower Reynolds numbers compared to other areas in the stream. The same study that I talked about earlier that found the endangered mussel species had preferred lower Reynolds number found similar results for. That had found low numbers for Froude's number had found similar results for Reynolds number. That they preferred low Reynolds number where the laminar flow was more likely. Another study done in Texas found similar results, and these together with other things indicate that mussels most likely prefer relatively smooth, non-turbulent flow. So I've talked about two complex hydraulic variables over the past 15 minutes or so, and how they may affect the habitat preferences of freshwater mussels. I hope you found this presentation relatively informative and enjoyable, and thank you.